So, you start a new project. Do you know what your tech stack is going to be? Do you know what your database is going to be? Do you know the difference between the databases? You've come to the right place. There are two classifications of databases that you're going to come across in day-to-day work: SQL and NoSQL. Now, SQL is actually a querying language, but ever since it was created in 1979, it's basically become synonymous with Relational Database Management Systems, or RDBMS databases. We'll get into exactly what that means in a second, but whenever you hear that, just think about those tables with the rows and columns. SQL databases also follow ACID, which is a set of transaction properties that ensure that the data is valid regardless of power loss, corruption, or other errors that might occur. ACID stands for atomicity, consistency, isolation, and durability. Atomicity means that if you make an insert or an update to your database, the entirety of your update or insert query will complete, or no data will be changed in your tables. That means if you have power loss in the middle of a query running or something like that, you will not get corrupted data. It's essentially all or nothing. Consistency guarantees that all the rights to a database follow a strict set of rules, don't compromise on table constraints, and every transaction that hits a database is queued in order of execution time. Isolation is how and when changes in the database are reflected to all the users, which ensures that a transaction completes before reflecting the changes in another transaction. And finally, durability ensures that any changes made to a database, once completed fully, are saved permanently. Wow, that sounds great, right? It does, but there's more to the story, and that's what brings us to NoSQL. NoSQL stands for Not Only SQL, and it expands on the classic structure of columns and rows inside of tables. Unlike SQL, NoSQL is not a querying language itself. It's a classification of database made popular by Web 2.0 companies in the 2000s and early 2010s. NoSQL champions quick reads and massive scalability, and has successfully found itself a home inside of tech companies around the world as sometimes even the de facto standard database in their technology stack. NoSQL databases don't strictly follow ACID, and we'll talk about why that's the case a little later on. But now that we know the difference between SQL and NoSQL, let's talk about the four types of databases that you're going to see in those two classifications. You have Relational Database Management Systems that we touched on before, document stores, graph databases, and key value stores. RDBMS databases include MySQL, PostgreSQL, MSSQL, SQLite, and many more. Now remember, these are the tables that store your information inside of columns and rows. Now, these are great for connecting a whole bunch of different tables with a single piece of information called a key. A good example of a key would be a user identifier that connects the private user data, such as email or password hash, to the public user data that a user would have to ingest when they're signing into an application or visiting an account page. Of course, there's a reason NoSQL has exploded in popularity, and this is because a lot of companies began writing a lot of data with the advent of Web 2.0 technologies like Facebook and Twitter. All of a sudden, they had to read and write terabytes of data every single day to serve content to the timelines of millions of users around the world within seconds of a web page opening. This brought many companies to the first pain point of RDBMS databases. They are very poor at scaling horizontally. That basically means if you want to increase the performance of your database, you have to increase the performance of the one machine that hosts that database. There are some ways to scale horizontally across multiple machines, but they're hacky at best, and it was never really designed for such scale. The second major pain point of RDBMS databases is that reading data can take a long time. Imagine for a second that you're an engineer at early Facebook, and you need to fetch the information for a post to be served on the Facebook newsfeed. You get your post identifier, you head on into the post table, and you get all the information related to that post. The content, the user identifier of the person that posted it, the time it was posted, any other metadata that might be important to the service. To make that look good on a newsfeed, you have to get that user identifier and attach it to a first name and last name. So you head on into the users table, you get that user identifier, and you get the poster's first name and last name. That's great, you combine that information, but what about the comments and the likes and the shares? Those are each in tables as well, and they each have user identifiers for the people that liked and commented and shared on that post. So you have to go to the users tables for each one of those and get the first name and last name of those people, combine all that data, and then serve that. All of a sudden you're combining tables from all over, and that's just for one post. Imagine for all the posts in the Facebook newsfeed, for every single user that visits Facebook in a day. And remember, all this is being served on one or two machines that are kind of beefy, but they're running all of Facebook. Obviously, this doesn't scale very well, and there are ways to make RDBMS databases read a little bit faster, and believe me, Facebook tried it, but that really wasn't the solution. The solution for Facebook was to move to NoSQL. That brings us to our next type of database, the document store. You could sort of think of a document as a JSON structure that contains all the information that you need for that piece of data. Using the same example as before, instead of normalizing the data by separating the shares, the likes, the comments, the user profile, and the content into different tables, what we're going to do is we're going to store all that information inside of one document. So if you know the post identifier, all you have to do is query the database one time and you'll get all of the information required to serve that content into a timeline. Examples of document stores include MarkLogic, Apache CouchDB, and the famous MongoDB. Now, each one of these are probably going to be using a different querying language to interact with their system, and they may or may not be a derivative of SQL. Some benefits of a document store are that you no longer have to follow that rigid structure of a table of columns and rows. Your data is a little more flexible and you could store it how you want on the fly. You also have the benefit of it being highly scalable across multiple machines, and reads and writes are generally much easier to a document store than something like an RDBMS. So it's all sunshine and roses. Nope. Horizontal scalability means that document stores have to compromise on ACID, putting data in harm's way of power loss, corruption, or just disagreements across multiple machines. Companies will do their best to ensure that the principles of ACID are still maintained inside their application, but in terms of database level, ACID's gone. Document stores also take up a lot more storage by denormalizing the data, which removes the need to reference multiple tables and documents in a database with a key to get information like user profiles or comments or something like that, but at the cost of repeating the same information over and over and over again. This speeds up the reads but costs storage in the long run. These aren't reasons why you should shy away from using something like MongoDB. It's a beautifully written database and it's used in tons of different areas. It's just you should understand the strengths and weaknesses of what you're going to use, and you should plan your tech stack accordingly. That brings us in to graph databases. Graph databases are basically a way of connecting nodes, information, with edges, relationships, to build a network of data points that can then be traversed. Examples of graph databases include OrientDB, Neo4j, and ArangoDB. Each of these will use their own querying language, but one of the more popular ones I'm starting to see is Neo4j's now opened Cypher querying language. Graph databases use graph theory to make relationships, or edges, within the graph first-class citizens to allow applications or users to really understand how their data points all connect to one another. This type of database is less about storing information, and it's more about understanding how the information connects to one another. A perfect example of this would be if we're building a friend service similar to Facebook's, where the friendship relationship is the most important or main focus of the application. What we can do is, if we understand which nodes or users have the friends relationship, we can better understand who a user knows and who they may know. And then we can offer suggestions based off of mutual friends as an example. I actually built 2 projects doing exactly this, and I'm going to make videos about it very soon, so stay tuned. Finally, we have key value stores. These have become increasingly popular recently thanks to those same Web 2.0 companies that need those super fast read and write speeds, because many key value stores will run entirely in system memory, acting as a caching layer in front of those old and slow RDBMS databases that places like Facebook and Twitter are still forced to use. Once again, these will not be incredibly popular in everyday projects, but you could sort of think of it like a hash table where you store some data using a key, and then you can later recall that data using that exact same key. A perfect example of this would actually be a tweet. So you would use your tweet identifier, you would query the key value store, and you get the exact details of that tweet. This is actually exactly what Twitter does, using a memory-based key value store called Redis. Facebook actually uses a similar system called Memcached, which has a pretty cool story attached along with it, where Zuck and a bunch of the early engineers at Facebook rewrote the application to be 64-bit instead of 32 so that they could utilize more system memory and store more information. A perfect example of a non-memory version of this would be MongoDB once again, or AWS's DynamoDB. Okay, that was a lot of information. What database should I use? you should probably use an RDBMS database for 90% of the projects you're going to create. The rigid structure of the rows and columns is probably exactly what you're looking for, and it's very unlikely you're going to saturate the read or writes on any database you're going to get your hands on for a little while. However, you should really take a look at what you're trying to create and see if there's a better alternative. You might find that a document store actually works better for your application. And those are the 4 main types of databases that you're going to come across in everyday projects. If you like this kind of information, please consider subscribing and give it a like. I actually have another video on my channel where I use an RDBMS database to build a vaccine locator for Canada. You can go check that out right now. Stay tuned for more content, and I'll see you later.